Hello, in this video I'm going to introduce our work on learning sparse representation with alternating backpropagation. Learning sparse representation has been a challenging and meaningful work in recent years. Sparse representations can encode latent variables with meaningful semantics of the original observation. We can easily explain the latent codes, and this will also lead to a more robust classifier. There are some related works, but with some limitations. Sparse coding mainly focuses on the linear mapping between the observation and the latent space. Alternating backpropagation can only learn dense representations instead of sparse latent space. Variational sparse coding uses approximate inference and it needs to design an extra encoder network. In this work, we present a new learning method to use spike and slab distribution as our prior belief. Spike and slab distribution can be viewed as a mixture of Gaussian. It has the similar idea as sparse representations, where most of the values are 0 or close to 0, while only a few of them have strong activation. We will then show how to incorporate this prior to our model to enforce sparsity on the latent variables. The framework of the model is briefly described in the figure. It is kind of similar to the EM algorithm. We first initialize the latent variables from the spike and slab distribution at each iteration. Then we do L steps of Langevin dynamics to obtain the posterior distribution of the latent codes while fixing the model parameters theta. At last, we will update theta using the obtained posterior distribution of the latent variables and also the given observations. The red lines here show the testing procedure. We can obtain reconstructed image and latent representation from the above steps. The spike and slab prior can help us inducing sparsity on the latent variables. When we update the latent variable using Langevin dynamics, the gradient of log prior is served as a regularization term, and it will penalize the latent variable. Given a small sigma 2, it is clear to see from the equation that when z is large, it is more likely to be sampled from cluster 1. While the z is small, it is more likely to be sampled from the cluster 2, and it will cause a larger gradient because of the small variance on the denominator, and thus a stronger power to push it towards 0, so the prior term will penalize small latent values and enforce sparsity in a certain degree. We conducted 4 experiments using MNIST and fashion dataset to obtain some preliminary results of our model. In the first experiment, we show that our model can enforce sparsity effectively on the latent code. We do so by changing the value of alpha 1 to see the effect on the reconstructed image. Here in the plot, we could see that as alpha 1 is getting smaller, our latent variable is becoming more and more sparse, and the reconstructed image seems to be preserving major information of the original image. We then demonstrate learned sparse representation can make the latent codes more explainable. We first obtain the latent representations of the observation, and then we change the value of one of the activated latent dimension and reconstruct the image using new latent codes. From the graph, we can clearly see that there are changes in the shoulder width of the cloth and the height of the shoes. We show that our model can indeed make the latent codes more explainable. Then we also perform quantitative experiments on the reconstruction error and classifier accuracy. We show that our model can achieve a smaller per pixel mean squared reconstruction error by comparing it to the VSC model with the same sparsity level. At the same time, it is not losing too much information by comparing it to the non-sparse ABP model. In terms of the classifier accuracy, we tested against various latent dimensions. We show our model can outperform other models and lead to a more robust classifier. In this work, we demonstrate the new learning method to learn sparse representation to increase explainability of the latent codes and the robustness of the classifier. We will explore more approaches in the future work, such as increasing the quality of reconstructed images and applying the current model to other complex datasets. This is the end of my presentation. Thank you very much for listening.